So here we have a situation where we have two conducting plates and a hollow conductor in the center, placed in the center. This is a conductor here. Imagine this is a Van de Graaff ball or something like that. Of course, we have uniform electric field between the plates. When it gets close to the center, we see this kind of pattern happening. And the charges, or you could think of moving charges distributing themselves on the conducting surface of this sphere. The negative charges closer to the positive plate, and the positive charges closer to the negative plate. And then we see an electric field that results something like this. Little bit of bending here. You may be asked to reproduce this in the tests. Let's have a look at another situation. Inside a hollow conductor, electric field inside a hollow conductor. So no electric field. There's only an electric field outside. And we looked at the reasons why. Essentially, if this is all positive charge, of course, if we put a small positive test charge in there, the arrow would be pointed outwards. It is. They look like little positive signs all the way around this conducting surface, distributing themselves evenly on the outside of the conducting surface. Of course, because of this positive charge, we have an electric field that's directed radially inward as well, away from that positive charge. But if you look on the other side, the same situation is happening, and we have a cancelling of the electric field inside. That's true in all directions, of course, if you can imagine this situation here. Okay. Electric fields near sharp points. So this is a little bit more interesting and a little bit harder to explain. Hollow conductor again, except it's a funny shaped hollow conductor. We have a large radius here. We have a very small radius here. There's a positive charge distributed not so evenly on the conducting surface. And you might notice that down here towards the smaller radius, there are more charges than there are per unit area at the large radius. And there's several explanations for this. There is still no field inside this conductor. The charges distribute themselves in such a way that the electric field inside is cancelled out by opposing charges. And also that they distribute themselves more widely spaced on the large radius and much closer at the small radius. And so as a result, we have a stronger electric field at the pointy end than we do at the not so pointy end. And you could look at the charge or the electric field per unit area here, given that box, and the electric field per unit area here, same area, a much stronger electric field, or a much more dense electric field apparently, which is true. Several explanations. It's actually, there's a student in the other class that is trying to come up with a vector diagram for how this works. I like to think of it as, imagine each of these charges here, just very simply so that you remember this fact. Each of those charges is a student, and each of these charges is a student also, and they're playing kind of a tug of war between each other. Okay, but then you say to the students over here, you guys spread out and you guys bunch up together. The net force from each side, if they were equally balanced in the first place, the force from each side would cancel each other out, wouldn't it? So if these students here were in a tug of war with these students over here, and nothing was happening, there was no motion, there was no net force on either side, and then you ask them to spread out here and to bunch up here, there would still be no net force either side. They still cancel each other out. They're just in a smaller radius. Okay, um, that's an analogy that's not perfectly true, but it helps for you to remember. Large radius, they spread out more. Small radius, they're closer together. The electric field is much more dense at the pointy end, at the small radius, and much less dense at the large radius. Last thing, and then we finish with the photocopier's application. Corona discharge. Does anybody know anything about corona discharge? Is somebody saying something about it or just talking? A discharge is the greatest word in the English language. Grossest. Oh, okay. If you're thinking in biology, yes. In physics, it's okay. Discharge means we just lose some charges. It's good. Corona discharge. Think about this situation. We have our Van de Graaff generator again, and this is just the ball on top. And the ball on top has a net charge all over it. It's covered in net negative charges this time. Distributed evenly around the outside of the conducting surface, as we've talked about. And I switch off the Van de Graaff generator. What happens to that Van de Graaff if you left it for 15 minutes and went up and touched it, do you think? Yes, exactly. So the main term there is discharge to the air. It should theoretically hold its charge, yet it doesn't. It's not sitting there isolated, is it? You can think of air particles around. There's air particles all over the place out here, okay? As you would know, if you move your hand fast enough through the area around you, you'll feel them, okay? It's a fluid. We're sitting in a fluid. We breathe that fluid. And those things are in constant motion. These little dots, these little air particles, they could be nitrogen or oxygen or whatever they may be, they strike this surface or get very close to it quite often. What happens when they do so? It doesn't stick to it. What happens when if I threw a piece of plastic, a plastic ball, a small plastic ball like a ping pong ball at the Van de Graaff generator sphere? Okay, yeah, it might repel it a little bit, but why does it repel it? So you're thinking ahead. I'd throw it at this sphere. It would probably strike the sphere because of its inertia. Then what happens to it? The ping pong ball will take some of that charge, won't it? It will pick up some, and then what? It bounces away and then takes it away, doesn't it? Exactly the same thing happens with the air particles. They strike that surface or get very close to that surface. When they get very close to this surface, okay, so they're doing it constantly, and if they weren't doing it constantly, we would not feel the 13 psi that we sit in here now, and our blood would boil immediately, okay? So 13 psi or thereabouts is striking, think of it as air particles striking this surface, and then they move away very quickly. Not because of momentum. They might do because of momentum, but also because of their charge. When they strike that surface, they gain a net negative charge, and then of course they're repelled by that surface quite quickly, repelled away. We call this a corona discharge. So the air particles boys at the front. The air particles strike the surface, gain a net charge of the same sign. So they're repelled away. The air particles are ionized, we say. And what happens to the metal ball? It loses its charge. As the air particles come in and strike the surface, they're ionized. They're repelled away because they now gain a net negative charge in this case. And they take away the charge of the metal ball. This is a discharging effect. We call this corona discharge. This is important in the application of photocopiers. The application of this topic, which is photocopiers.